Hello everyone! Ever wondered if we could predict a nation's Olympic medal haul just by crunching some numbers? Today we're going to do just that using machine learning. We're going to predict how many medals a country might win in a given year using a few key inputs. Enter number of events, the total number of unique events the country will participate in. Enter number of female athletes, the number of female athletes representing the country. Enter number of male athletes, the number of male athletes representing the country. Enter number of previous medals, the number of medals the country has won in previous Olympic Games. Based on these inputs, we'll predict the number of medals the country is likely to win this time around. Let's see how it all adds up. Project setup. Importing libraries. We start by importing the essential libraries needed for our project. These libraries will provide us with the tools to analyze, process, and model our data effectively. Next, we load the dataset containing athlete information and the NOC regions. This data will serve as the foundation for our analysis and predictions. Data exploration and pre-processing. Explore the athletes and NOC dataset. To get a good grasp of the data, we first obtain a concise summary of the athlete's data frame with the info function, and then a statistical summary using the describe function. These steps help us understand the structure and content of our dataset. Handle missing values. Missing values can be problematic, so we take steps to address them. Check for missing values. We identify where missing data exists. Drop rows with missing values in the athletes and NOC dataset if necessary. Impute missing values in age, height, and weight columns with their respective means to maintain the dataset's integrity. Fill missing values in the medal column with none, ensuring that our analysis isn't skewed by missing data. Merging datasets. We merge the athlete's dataset with the NOC region's dataset to bring all relevant information together. The NOC column is replaced with region for clarity. We combine team and NOC columns into combined team to create a unique identifier for each team. Finally, we standardize the text data in columns like combined team, city, sport, and event to ensure consistency. Dropping duplicates. Remove duplicate rows to avoid redundant data. We also remove remaining duplicates based on specific columns, further refining our dataset. Visualize and identify outliers. A box plot or box and whisker plot is a powerful tool for visualizing the distribution of a dataset. It highlights the minimum, first quartile Q1, median Q2, third quartile Q3, and maximum values. By plotting these, we can easily identify the spread and skewness of the data. Outliers in a box plot are particularly useful to identify. These are data points that fall outside the expected range and can be spotted visually as they lie beyond the whiskers of the plot. We plot box plots for age, height, and weight to check for any unusual data points that might need further investigation. Use z-scores to identify and remove outliers. The z-score helps us understand how far a data point is from the mean, measured in standard deviations. We calculate z-scores for age, height, and weight, which standardizes these columns, making it easier to identify outliers. Outliers are identified if their z-scores are greater than 3 or less than -3, meaning they are far from the average. We then filter the data frame to keep only the data points that fall within this normal range. Once outliers are removed, we drop the z-score columns as they're no longer needed. Manual check for unusual values. The code checks and displays all unique values present in each specified categorical column of the athlete's data frame. This helps us understand the range of categories and spot any inconsistencies or unusual values. This step is crucial in the preliminary stages of data analysis to ensure we have a clean and understandable dataset. Frequency distribution for each categorical column. Understanding how often each category appears in our dataset is essential, so we calculate the frequency distribution of values in key categorical columns. This helps us spot any imbalances or patterns in the data, ensuring we understand the distribution of our categories. The value counts function returns the frequency of each unique value in a column. It sorts the counts in descending order by default, so the most frequent values appear at the top. Feature engineering. OneHotEncoding. OneHotEncoding is used to convert categorical variables into a format that our machine learning model can understand. For example, we apply this technique to the gender column to create binary columns for each gender. This conversion ensures our model interprets the data correctly. Grouping data. Grouping the athlete's data frame by year and combined_team, we aggregate statistics like average age, height, weight, and the number of unique events and medals won. We also sum up the number of male and female athletes, giving us a clear picture of each team's composition. Getting previous medal count. By adding a column to track the number of medals a team won in the previous Olympic year, we create a useful feature for our model. This column is filled in a way that ensures the data is chronologically accurate. Correlation matrix. In machine learning, understanding the correlation between features and the target variable is crucial. Features with strong correlations are often better predictors. We visualize this correlation using a horizontal bar plot, helping us identify which features are most relevant to predicting medal counts. Verifying correlation using regplot. We generate scatter plots with regression lines for each feature to visually assess their relationship with the target variable. This step confirms which features are worth keeping for our model. For instance, we observe that age, weight, and height have low correlations with the number of medals, indicating that these might not be strong predictors. Drop columns with low correlation. To simplify our data frame, we drop columns like age, weight, and height, which have low correlations with the target variable. This focus on relevant features will help improve our model's performance. Model building. We separate the features from the target variable to prepare for training. Next, we split the data into training and testing sets with 80% for training and 20% for testing. Feature scaling is applied to ensure that all features have a mean of 0 and a standard deviation of 1. This is particularly important for linear regression models. We then train a linear regression model on the scale training data, allowing the model to learn the relationships between the features and the target variable. Model prediction. The trained model is used to predict the number of metals for the test data. We create a new data frame combining the test features with the actual and predicted metal counts, allowing us to compare and analyze the model's performance. Model evaluation. We evaluate our model by calculating the mean absolute error, MAE, and R-squared, providing insight into the model's accuracy. MAE measures the average error in the predictions, while R-squared indicates how well the model explains the variance in the data. This code is used to extract and display the coefficients of the features in the trained linear regression model. These coefficients provide insight into the importance and impact of each feature on the model's predictions. Model deployment. To make our model reusable, we save the trained model in Scalar to a file using Python's pickle module. This allows us to load the model later for predictions without retraining it. Load and use the model. Finally, we load the model in Scalar from the pickle file. And create a simple user interface to take inputs and predict the number of metals based on those inputs. Find the dataset and code in the description below. I trust you found this video helpful. Thank you.